So, in the last class we derived the transfer function for a linear discrete time model, basically using an ARMA model. So, we will just go one step further into the discrete time model and derive the state space model here. So, let us consider the case when P equals Q. I mean, this is without loss of generality. If P is lesser than Q, then we can take Q states. If P is greater than Q, then we can take P states. So, let the transfer function h of z be given by y of z by x of z, and this is basically the numerator polynomial which is given by sigma k equals 0 to p b suffix k z power minus k divided by this denominator polynomial which is 1 plus sigma k equals 1 to p a k z power minus k, right. And then we have the transfer functions which are related as follows. So, y of z by w of z is basically this numerator polynomial which is in B, and the denominator polynomial is w of z by x of z which is given by this polynomial. So, the first and the foremost step is to basically form a signal flow graph which represents the above transfer functions. So, we start with the input which is x of n, right, and this is basically it goes through a delay line, and we have p equals qk. So, basically we have p number of delay elements. So, z power minus 1 is one delay element, like this we have p such delay elements. In the forward path we have all these b's of i's which are connecting these outputs from the tap delay line. So, w of n is just at the output of the summer, and this goes through this gain b naught and then goes to the output of the summer here y of n at the output summer. Then again from the output of the first delay line you have basically a feed forward path which is through the gain b1, and then there is a feedback path which is through minus a1 which is going back to the input. The feedback path leads into the input here, and feed forward path goes to the output. So, like this we have b2 which is at the output of the second tap delay line, and it is connected to the output, and minus a2 is basically is a feedback path going back to the input, and this is going on forward till we have the gains bp and minus ap which are basically the feed forward and the feedback paths which are connecting the output and the input. Now, what we need to do is basically to formulate the state variables. Okay. So, the first observation that you need to make is the following. So, you have the signal Wn here at the output of the summer here, and after p such delay elements this signal here is w of n minus p, right. This is straightforward. Now, let us start formulating the state variables. Now, we will start with w p of n, and we define this to be w of n minus 1. So, if you look at the output of the first delay element, that is Wn, when it is filtered through the first delay you get Wn minus 1, and that Wn minus 1 I call it Wp of n, okay. And Wp minus 1 n is basically W of n minus 2, so on and so forth, and we have W1 n which is W of n minus p. This is a very important step. So, what we have done here is very simple. As the signal Wn is passing through the delay line, we are tapping the outputs of the delay line and we are formulating them as state variables. So, these are basically the hidden states of the system. Now, as the signal Wn passes through the delay line, the state variables W1n so on till Wpn, they form a vector. It is very important, they form a vector. So, this is a very important concept because a signal through a delay line can be transformed to a vector in a space. So, the conventional notion of what we think about as patterns in space can now be thought of using signals through a Tabb-Delay line, right. So, this is basically the time to space mapping which dictates that the signal in time can be transformed to a vector in space, and the signal dynamics can be visualized as a trajectory as below, right. So, we have W1 of n plus 1 is W2n, so on and so forth. Wp minus 1 of n plus 1 is Wpn, right, and Wpn plus 1 is basically this point, which is I said Wpn is Wn minus 1, right, and Wpn plus 1 is basically your Wn, which is basically x of n minus all the terms that you have in the feedback path. So, which is basically x of n minus a1. So, you have x of n. So, Wn is the signal which is x of n minus a1 times Wpn minus a2 times Wp minus 1n, so on and so forth till minus ap times W1n. Now, let us form a state vector which is Wn, as I told you, which is capital Wn, which is this vector which is W1n so on till Wpn, and we have these interim state variables which are described as follows, right. So, now using this set of equations that we formulated here, right, we will try to connect them in the form of a matrix equation. W of n plus 1 is some matrix A times W of n plus some vector B times x of n, where this matrix A has this form, and B is basically all zeros followed by 1, which is basically comprising of P elements, P element vector. It is very straightforward. I mean, if you just look into the set of equations that are here, right, if you look at the set of equations here and rewrite them using the matrix form, you get this equation, which is very, very simple. Now, we can do the math for expressing the output y of n through a sequence of equations as below. So, what we have is as follows. So, our y of n is basically b naught times w of n plus summation bk wp plus 1 minus k of n. I mean, these subscripts you should just carefully observe as you see through the signal flow graph. Now, we do a little bit of careful math here, some simplification through algebra, which is b naught times wp of n plus 1. Recall wn is basically wp n plus 1 plus summa k equals 1 to p bk wp plus 1 minus k of n, right. We have this equation. Now, we use wp of n plus 1 that we derived earlier. I mean, this is basically we have this equation here which relates x of n and the rest of the parameters. So, once we do that, so y of n is basically b naught times x of n minus a1 wp of n minus a2 wp minus 1 n so on till ap w1 n plus all the rest of the terms that you have from this summation. So, we now have expanded w of n in terms of your coefficients b of I, then x of n, then your other coefficients which are ai's, and then writing it in a compact form, we have y of n is basically summa k equals 1 to p bk minus b naught ak times wp plus 1 minus k of n plus b naught x of n. So, this is this equation. Now, this is a scalar, essentially b naught x of n is basically a scalar, and if you think about the summation, this can be thought about as an inner product between the state vector Wn and some vector C with p elements that are described as follows. So, this vector C is basically given by this form. The first element is Bp minus B naught AP and so on, the last element is B1 minus B naught A1, right. So, now we have all our variables that can describe the state space model, because the important parameters are these C's and D's which link the state variable state vector W of n and x of n to the output y of n, and we have the matrix A and the vector B that link the state vector at time n and the input to the state vector at time n plus 1. So, now we have all the ingredients that can describe the state space model, and this is the most general form that we have, and this representation is very useful for you to simulating discrete time systems given arbitrary inputs and transfer functions. With this derivation we are ready to go into the time domain equivalent of this formula. So, in the time domain we can write the state vector Wn in this form, which is a power n W0 plus summa k equals 0 to n minus 1 a power k times this vector B times x of n minus 1 minus k and the output is y of n, which is C transpose into Wn, this is a vector plus d times x, and you plug in Wn from the earlier step, and then you can simplify the rest of the equations. I hope this is clear to all of you. Okay. So, basically we should know what is the derivation. The derivation is a very important point, because it tells you to relate the input and the output through a state vector. And how you define the state vector, because state vector representation is not really unique. I mean, different people can have different ways in which they can define the states at different takeoff points. So, therefore, each of your answers would be different if one were to ask you to get the state variable representation and derive the transfer function, but the transfer function has to be the same, though the rest can be different. Okay. So, with this I will give you a short exercise. Suppose I give you a transfer function h of z, which is 1 plus 2 z power minus 1 plus z power minus 2, or 1 minus 0.75 z power minus 1 plus 0.125 z power minus 2. And suppose you have x of n is 1/2 power n u of n, obtain the state variable representation and study the output response A mathematically via simulations, verify these results by any of your favorite undergraduate methods. Studied in DSP. You've done different methods for figuring out the output given the input, right? You have done many techniques. So therefore, what I want you to do is obtain the state variable representation for this transfer function, study the output response mathematically. Then once you have the state parameters, write a short MATLAB code where you can simulate the system. What you do in simulation should be exactly what you do mathematically, right? And then verify these results by any of the methods you have studied in your undergraduate DSP course. Okay, clear so far? Based upon the state variable representation, we are ready to derive the transfer function. From state variable representation. So what we have to do is basically start with the equations we had earlier. W of n plus 1 is basically some matrix A. I think I probably would want to use a different color for this matrix. A times Wn plus some vector. So let me also use a different color for this vector, plus B times x of n. X of n is a scalar, but we could have a vector also for this. Then we have the output y of n is basically C transpose Wn plus D times x of n. Now we have these pairs of equations, right? Now we have to derive the transfer function. So let us apply the Z transforms to equations A and B, right? So Z times W of Z is basically A times W of Z plus B times x of Z. This is a vector. And then y of z is C transpose Wz plus D times x of z. Okay. Now I can rewrite this equation. Let me call this equation 1, let me call this equation 2. So I can rewrite equation 1 in this form: Zi minus A times Wz is basically B times x of z. Right. Remember, A is a matrix. We cannot write simply Z minus A, right? There is an identity matrix there, Z times identity matrix. So this is what we have, and therefore let us call this equation 3. Now we can use equation 3 and we can plug it into 2. We will end up with Yz is basically C transpose times, we have to replace this by Wz here, which is basically Zi minus A inverse times B x of z plus d times x of z. So this is going to be this. Okay. Now we are ready to derive this transfer function. Basically we say Yz by x of z is equal to h of z, and this is given by into Zi minus A inverse B plus D. So this is the familiar form that most of you might be used to for the transfer function of the state variable representation. Clear? So basically you can go with, if you have a linear time invariant model, you can get the state space representation, and your state space representation can be different from what somebody else may have depending upon how you have formulated your state variables, but your transfer function has to be the same. Well, there should be an underscore here consistent with the previous equation. We may question the conditions under which this inverse exists. I think I would just say that if inverse exists. So we will stop here for this module, and then we will show the equivalence.